In the last video, we introduced this extremely important definition that's going to be the foundation of this entire section, and most of the sections to come. We saw that in this definition, we defined this nth partial sum, this sequence S sub n. And we're going to see that this sequence, again, is going to be used to help us determine if an infinitely long addition problem is going to converge or diverge. Let's take a look at how this works down here in example number 1, when we look at this infinitely long addition problem. Notice this is the addition problem of 1 plus a negative 1, plus a positive 1, plus a negative 1, plus a positive 1, plus a negative 1, just on and on for the rest of time. So does this series actually converge? What does it converge to? Does it add up to be something? Well, according to our definition, if we want to go ahead and figure this out, we're going to need to go and look at our different partial sums. So I'm going to try to go ahead and find the first, second, third, and fourth partial sums of the series, and then see if I can reach maybe some sort of a conclusion. Notice if I want to calculate S1, that would say add up the first item in the addition problem. Well, notice that doesn't really give me much. That's really just saying get the value of 1, and that's it. So my first value, my S1, is just 1. Now to find S number 2, there's a little bit more work to do, because that says take the first two items in the addition problem, which is the 1 and the minus 1, and add those up. Of course, that results in a value of 0. And so I see the sum of the first two items is 0. I can oftentimes think of these S's as kind of like a running total on the infinite addition problem, like how much do we have accumulated thus far? So here it's kind of like, what's the grand total after I have had 3 items in the addition problem? Notice these would be the first 3 items, and the grand total result is just going to be the value of 1. S number 4, that's going to be given here as 1 minus 1 plus 1 and then minus another 1, which of course is going to leave me back again with the value of 0. So I can start to see here kind of what this sequence of S is actually looking like. So I can see here that my S sub n sequence actually looks like these sets of values. 1, 0, 1, 0, and I can probably pretty easily see that this is just going to continue to happen endlessly, right? This is the sequence that I have. And according to the definition up above, if this sequence here in green converges, then this addition problem converges, and they converge to the same value. And if this sequence diverges, then the addition problem diverges. Again, that should make a lot of sense, because what we're interested in doing in the addition problem is to say, I want n, the number of things that I'm going to add, to approach infinity. Right? That's what we're interested in. I'm even going to write that here. So I'll say we will calculate the limit as n, the number of things in the addition, goes off to infinity. And so when we look at this, we can probably start to really easily see if I take this out to forever, then I'm really going to get a result that just does not exist, since my S sub n oscillates between the values of 0 and 1. Right? So if this limit doesn't exist, then that means that our green S sub n, our partial sums, that sequence of partial sums, is divergent. And so the given series, that is that given infinitely long addition problem that we had up here at the start, is also divergent. And we have an answer, right? So I can determine rather quickly that this series is going to be diverging, because I'm looking at the running total, and that running total isn't accumulating to anything. Well, let's take a look at another example to see how this would work. Let's try the same sort of thing down here. I want to go ahead and find the first, second, third, fourth partial sums, but of this infinitely long addition problem. So to start off, let's see, I'll find S number 1. S number 1, that'd be the sum of the first item here. Now the first item in this list appears to be 1/2. Okay, I can then go ahead and try to find S number 2. Notice that S number 2 is going to be taking a 1/2 and adding on to it. Let's see, I can plug a 2 in to get the second item in the addition problem. And that would be the value of 1/4. Now if I add these values together, 1/4 and a half creates a total of 3/4. Okay, S number 3, and I can also get ready for S number 4 down below. S number 3 is going to be, let's see, a half plus a fourth plus, I think the next number out of that list would be an eighth, right? That's what I get when I is a 3. Okay, so let's see, the first two things add up to 3/4, which is the equivalent of 6/8. And so that means that as a grand total, this is going to be 7/8. Okay, great. Let's find the fourth partial sum. So that's going to be adding up the first 4 items. My fourth item would be when I plug in a 4, and that gets me 1/16. So notice, the first 3 items added to 7/8. That's the same as 14/16. Adding on one more brings me up to 15/16. Now, something interesting kind of happens here with the sequence as I begin to write it out. I can't quite say for certain, without doing a direct calculation, what the next number in this sequence is going to be. I mean, I know I can continue to write out more and more things, but I don't know exactly at this moment what's coming next. Whereas like up here, it was so easy to kind of abstract from this addition problem. But down here, things are a little bit more complicated. So if I want to calculate the limit of this, that is, I want the limit as n, the number of things in the addition problem goes off to forever, but when I try to calculate this, I mean, what the heck does it make? I could start to guess, but notice that that's really hard because I can't say that this limit doesn't exist, and anything else besides that is just really a guess. Now, I could probably make some educated guesses, right? Maybe you might think, hey, you know, the numbers in this list seem to be getting closer and closer to being 1. But does that mean that they do get closer and closer to 1? Maybe they actually get closer to 1.000001, right? So it's like, I don't know for certain what these things are adding towards. This is where we can see that it's really difficult to find this limit, and I can state that we will need a formula for S sub n if we wish to calculate this limit. Right? I would need some sort of a formula. So this could become like what we saw in the past couple sections, right? Where I could do limits of sequences. But I had to have like S sub n is equal to, you know, n over n plus 2. You know, like I needed a formula for it. And I don't have that. Now, it's actually totally possible to show that this series here actually does add up to 1. And it is even possible to find this formula for S sub n. We'll see how to do that a bit later. But at the onset, when I tell people that this series here actually does equal 1, sometimes they're a little bit confused. Like, wait a minute, you said, Kyle, I was going to add infinitely many things together. If I sit on my calculator and I just keep punching in buttons, and right, and like, won't I just constantly be accumulating more? How could I ever just kind of end at a value of 1? Well, to kind of help demonstrate that, I'm going to go ahead and really quickly here think about like the following picture, just to kind of illustrate that it is possible to add infinitely many things together and get to a finite amount. Let's suppose that I have a square that actually has side lengths of 1 and 1. So again then, I can easily see that the total area of the square is 1. Now I'm going to go ahead and I'm going to start shading in portions of this square. I'm going to start by taking my square and just chopping it in half right down the middle. And I'm going to shade one portion of the square. Right, 1/2 over there. So notice I have 1/2 of the total square shaded. Okay. Now I'm going to go ahead and I'm going to take the remaining half that I have over here. I'm going to chop that in half, and I'm going to shade this. So notice I just took 1/2 of the square, and I added on 1/4 of the square. Notice that's actually exactly what we were doing here. Well, now I'm going to take this 1/4, and I'm going to chop that in half. That would make 1/8. And I'm going to add on that 1/8. And then I'm going to chop what's remaining in half, and I'm going to shade in that. And I'm going to chop what's remaining in half, and I'm going to shade in that. And I'm going to chop that in half and shade in there. And if I was to continue to do this for the rest of time, any idea how much I would ultimately be shading? Well, notice if I stop the shading process at any point, I definitely would have a total amount of shaded space of less than 1. But if I never stop, if I let the number of shading pieces go off to forever, then I would clearly see I'm going to be shading the whole square, and I'm going to be shading a grand total area of 1. So very interestingly, I can do something infinitely many times and yet not accumulate an infinite amount of something. That's a very, very interesting idea. Now, what we'll see in the next video is that sometimes it will be crucial that I am able to find a formula for this green S sub n, because if I want to calculate this limit, I need that formula. And I can't always rely on some sort of intuitive picture to help me understand how an addition problem like the one that we have shaping up here could actually equal 1. We'll come up with a more rigorous idea for why this addition problem does add up to 1 a little bit later in this section.